You know, every single day, we're using software that is just unbelievably complex. I mean, think about your web browser, your phone, all of it. But hidden deep inside all that code are some pretty nasty bugs, kind of like little time bombs just waiting to go off. And behind the scenes, there's this invisible race going on to find those bugs before the bad guys do. So today, we're going to dive into a really clever new technique that's totally changing the game.
Right, so how does this actually happen? How do we find these critical bugs before they can affect you and me? I mean, the software that runs the modern internet, like the JavaScript engines in Chrome or Firefox, we're talking about hundreds of thousands of lines of code. You can't just have a person read through all of it. It's impossible. The answer is something called fuzzing, which is basically just automatically throwing thousands and thousands of different inputs at a program to see what makes it crash. But as we're about to see, not all fuzzing is created equal.
The real heart of the problem is this thing called an interpreter. The easiest way to think about it is like a professional translator living inside your browser. When a website sends a JavaScript code, the interpreter's job is to translate that code into actions. You know, the stuff you actually see on the screen. But here's the catch. This translator is also a really, really strict gatekeeper. And that's where the dilemma for security researchers really begins. Okay, so here's the crucial point. These interpreters are incredibly picky. They have a very strict set of rules, a grammar, for what they consider valid code. So if you just throw a bunch of random junk at them, they take one look, say, nope, this is nonsense, and just spit out a syntax error without ever actually running the code. This means you never get to test the deeper, more interesting parts of the program where the really nasty bugs are probably hiding.
So, this whole dilemma has led to two main strategies for automatically finding bugs, this fuzzing process we mentioned. But you're gonna see that both of them have some pretty big flaws.
On one side, you've got byte-level fuzzing. I love this analogy. It's like a monkey randomly banging on a keyboard. It just changes individual letters and symbols. It's super simple, but it almost always produces that total gibberish we talked about, and the interpreter just rejects it immediately. Then, on the other side, you have grammar-based fuzzing. This is the strict grammarian. It knows all the rules of the language, and it only generates perfectly valid, grammatically correct code. But here's the problem. Some of the most clever and dangerous bugs are actually triggered by code that's almost right, but it breaks the rules in a very specific, very weird way. The strict grammarian would never even think to write something like that.
And look, this isn't just a theory. This chart from the research paper says it all. When they tested a standard byte-level fuzzer, this one's called AFL, you can see it had a success rate of just over 10%. Just let that sink in for a second. That means for every 10 things it tried, 9 of them were immediately thrown out as garbage. 90% of its effort was completely wasted before the real testing could even get started. So, if one method is way too random and the other is way too rigid, what we really need is a Goldilocks solution, right? Something that's just right. And that brings us to this new idea that finds that perfect sweet spot in the middle. It's called Token-Level Fuzzing. And the core idea is, honestly, it's beautifully simple. Instead of changing individual letters, it changes whole words, or as programmers call them, tokens. It'll swap the word if for while, or maybe a plus sign for a minus sign. The best analogy is that it's like playing Mad Libs with a computer program. The sentences it creates are often grammatically weird, sure, but they're built from valid words. And that gives them a much, much better chance of tricking the interpreter into revealing some kind of hidden bug.
Okay, so the concept is super clever, but how does it actually work in practice? Well, the process is surprisingly elegant.
It all starts by tokenizing, which just means breaking a piece of valid code into its basic parts, all the words and symbols. Then, here's the brilliant part. It encodes each unique token into a number. So suddenly, this complex piece of code is just a simple list of numbers. And that makes the fuzzer's job incredibly fast and easy, because it's way simpler to mess with a list of numbers than to try and understand lines of code. After it shuffles the numbers around, it decodes that list back into a new weird piece of code and then just runs it, watching closely to see if anything crashes.
And this isn't just me simplifying things for you. What's so cool here is that this is the actual architecture from the research paper. You can see that fuzzing engine right in the middle doing all of its work on those encoded numbers. It doesn't speak code at all. It only translates its work back into JavaScript at the very last second to see if it hit the jackpot and found a bug. That's the real key to its speed and efficiency.
All right, so we've got a clever idea and an elegant way to do it. But at the end of the day, this is cybersecurity, and the only question that really matters is, does it actually work? Can it find real, undiscovered bugs in the software that you and I use every single day? The answer is a huge, resounding yes. They put it in a 72-hour cage match against 4 other top-of-the-line fuzzers, and token-level fuzzing was the undisputed champion. Just look at that bar on the far left. It didn't just win, it found significantly more unique bugs across multiple JavaScript engines than any of its competitors. It wasn't even close.
And the total haul from this whole research project is just staggering. 29, that's 29 previously unknown bugs discovered in the actual JavaScript engines that power Chrome, Firefox, and Safari. These were real, hidden vulnerabilities in software used by billions of people every day.
The researchers themselves really summed it up perfectly. The power of this approach is that it lives in this unique middle ground, and that allows it to discover entire classes of bugs that were basically invisible to all the old tools.
Okay, let's look at a perfect example of this in action. This tiny little piece of code found a serious memory corruption bug in V8, which is Google's JavaScript engine. Look really closely at that line with super. See that extra number 1 just kind of hanging out there after the parentheses? That's a syntax error. A strict grammar-based fuzzer would never ever create that code. But token-level fuzzing, in its chaotic, Mad Lib style, just stumbled upon it and revealed a critical vulnerability. Its greatest strength is its ability to be wrong in exactly the right way.
So what does all this mean for you? Well, first, it means safer browsing. This technique is like putting a much smarter guard at the very front gate of your browser, one that can catch threats the other guards would totally miss. Second, it really shows that security is a team sport. This tool doesn't replace the old methods. It finds the bugs that they're blind to, and that makes our defenses stronger overall. And hey, this isn't just theory. This research led to over $10,000 in bug bounties and real security patches in the browser you're probably using to watch this right now. Token-level fuzzing is, honestly, a brilliant leap forward. It's a great example of how a simple, clever idea can solve a really complex problem. But it also makes you wonder, right? As our software just gets exponentially more complex, what's the next Goldilocks idea going to be? What other creative, out-of-the-box approaches are we going to need to invent to stay one step ahead in this constant battle for cybersecurity?